Hey, differential equation students. So now we're going to do lesson 31F, and it has to do with systems of differential equations and the degenerate case. So just like with algebraic systems, you can get one answer, or you can also get no answers, or infinitely many answers. And the same thing happens for differential equations. And so it's a really short lesson, but it talks about what happens if you have one of these cases where either you get no answer at all or infinitely many. Lesson 31F, the degenerate case. So remember back in algebra, when we solve systems of equations, you could find, a ordered pair that would make the system true, but it was also possible to find, to have a system where no ordered pair would work, or another system where any ordered pair that worked for one equation would also work for the other. Well, guess what? Since we have systems of differential equations, then the same situation is going to happen. So let's look at this example. If I say the derivative of x minus the derivative of y equals 1, and then my second equation is the derivative of x minus the derivative of y equals t squared. So in order to do, let's eliminate x to begin with. So I'm going to multiply this through by a negative. And when I go ahead and add those two lines together, then the x cancels out, but so does the y. And so now I don't have any x or y. I have a 0 on that side, equals a negative t squared plus 1. Now, while I can solve this to make this true, I don't get any equations out of it. So I don't know, I don't have any information on x and or y. And so in that respect, this is saying there is no equation to be equal to a negative t squared plus 1. And so in this case, this is going to be no solution. Let's get another example. What if I change this slightly, say derivative of x minus the derivative of y equals, say, t in this case, and then my second equation is 7 derivative of x minus 7 derivative of y equals 7t. So again, we're going to go ahead, multiply the bottom one by a negative 1. It will, we have to multiply the top one by a 7. And so now our new, when we solve that, we get a 7 dx minus a 7 dy equals 7t, and a negative 7 dx plus a 7 dy equals a negative 7t. And in this case, everything canceled out. And so in that case, we would get 0 equals 0, while this one says it's always true. And so this one would say that if one of the differential equations is true, then the other one's definitely going to be true also. And so this one has infinite many solutions. So this has infinite many solutions. So I guess the next question becomes, can we show the relationship between the two with those infinite many solutions? And so we're going to do a trick, and sometimes the trick works. So we're going to take either one, really, but I'm going to take the top differential equation, and I'm going to go ahead and factor out that derivative. And so I get x minus y. The derivative of x minus y is t. And I'm going to do a u substitution. For u is x minus y. When I go ahead and do that, then I get the derivative of u equals t, and I can integrate that on both sides, separation of variables, and I get u is t squared over 2 plus my integration constant, and back substituting, I get x minus y is t squared over 2 plus c. And so what that tells me is my x equation is going to be whatever my y equation is plus t squared over 2 plus my integration constant. So now I can arbitrarily pick whatever y equation I want to make, and I know what the relationship between, and then I can go ahead and say what the x equation is from that. As I said, not an earth-shattering lesson, but just a good thing to note. As always, if you guys have questions, please let me know.